So there are univariates here, there are bivariates, and there are trivariates, multivariates, things like that. There will be many properties of these polynomials that will be of interest to us throughout the talk. So two properties for now that we go to keep track. It's K. So degree is total degree throughout the talk. The other property is going to be sparsity, which is the number of non-zero monomials in a polynomial. So what's the sparsity of this?
What is the sparsity? Can you?
Yeah, it's the number of non-zero monomials in a polynomial. You can always write this polynomial as 0 times x to the 5 plus 0 times x to the 27 plus 0 times, you can add a bunch of zeros. But we'll count the number of non-zero monomials in a polynomial, non-zero terms. So this has 3 non-zero terms, this has 1, 2, 3, 4, 5 non-zero terms, this has 5 non-zero terms, and this has, how many non-zero terms does this have? How many non-zero monomials? It's n choose k. Right. Good, so are we good? So degree and sparsity. For now, these are the properties of interest. The main questions in this area, so this is sort of a, in computer science is a relatively young research area, 50, 60 years old. And this is one of these older questions that people had thought about even before CS in its current form was around, which is to design efficient algorithms for this problem. So I give you a polynomial and I ask you to output its factorization into irreducible factors. That just means you try to factor things as long as you can factor things. So given a polynomial, find its factorization. This is a question. Most of you would have seen some version of it. This in middle school, high school, 7, 8. Okay. And typically those questions are for univariate polynomials. So for now, let's stick to univariate polynomials, but we'll move on to multivariate. You can ask these questions for multivariate polynomials. They make perfect sense. For instance, if I'd asked you to factorize this polynomial, this factors this. This is the kind of example we usually see in school, at least I used to see. People here seem to see for last year, so clearly things have changed. Yeah, here's another one. This is also sort of an example that you'll see. This is a nice example. So x to the n minus 1, this is true for all n, or at least all n, at least 1. So this factorizes as x minus 1 times 1 plus x squared and so on. This is a good example to keep in mind. Keep this in mind. This is something that will keep showing up again and again. What about x squared plus 1? How does this factor?
Maybe complex numbers.
Right, but we are over rational numbers, so it doesn't factor over rational numbers. It's irreducible. It doesn't break further over rational numbers. But if you are allowed to work over complex numbers, then you can further break it into x plus omega, x minus omega, x plus. What about this? Yeah, I mean, it takes a couple of minutes to see that you can't factor this either. This does not factor. In fact, I don't think it factors even if you go to complex numbers. It doesn't factor. Polynomial structure presents. So, right. So the first question of interest generally throughout this talk would be to design efficient algorithms. This is something people were thinking about in the 70s. And the other question is to understand. The other set of questions focuses around understanding the structure of factors of polynomials. And typically this looks like questions here are of the following form. If a polynomial is nice, then are its factors also nice? What does nice mean? Well, nice could mean whatever properties of your polynomial you are interested in. So for instance, if a polynomial has low degree, do its factors have low degree? Is it true? This should be true, right? This is true. Great. So for degree, if your notion of niceness was the degree of a polynomial, then this is obvious. What about if the notion of niceness is the sparsity of a polynomial? If your polynomial doesn't have too many non-zero monomials, it has low sparsity. Is it true that the factors also have low sparsity?
No.
Right. So some people say no. So we'll get to this at some point. But this is the kind of question. These are instances of this family of questions that are of interest. There are other flavors of this question. So sometimes the questions look like, suppose you have a polynomial that's easy to compute, whatever that means. And maybe there's a fast algorithm for evaluating your polynomial at a given input. Does this mean that there's a fast algorithm to evaluate your polynomial at the factors of your polynomial at a given input? And similarly, you can not just fast algorithms, you can also fast parallel algorithms. Again, whatever that means. But you should have some vague picture of what a parallel algorithm means. It's an algorithm that runs in few rounds, does things, and then you are done. It's not sequential, it's parallel. Great. So this is the second family of questions that were of interest, and I mean we have seen examples which seem to address some of these questions. Right. So this polynomial x to the n minus 1, this factorization. What does it tell us about any of these questions? Does it say something about any of these questions? Yeah, it says something about sparsity. This is a polynomial with sparsity 2. But here is a factor which has, it has n monomials. So it grows, the sparsity grows significantly when you go to factors. This is the multivariate version of this example. So you take this polynomial, take it on n different variables, multiply them out. The factorization also multiplies correspondingly. And then you can talk about sparsity of this polynomial and sparsity of these the factors. Again, we'll come back to this. But are we good so far? The kind of questions that are of interest. Great. So what's this talk about? So mostly it would be about the question of structure of factors of nice polynomials or various notions of niceness. We will introduce definitions of niceness and talk about what this means. We'll start with some examples of such questions for univariates, and then we'll go to multivariates, and we'll talk about multivariates. I'll also spend a few minutes on applications of these questions. So what are potential applications? And there are very deep applications to questions like this in computer science. And most of the talk will hopefully not be very dense. I didn't know what audience I was talking to. And most of the talk will be about old results that I like many years ago. I will mention some recent work on these things, but mostly we'll talk about those. And I have some slides for a sketch of proof of something towards that, but if there's time, this is not high priority. So like I said, please ask questions. Stop me. Alright. Good. So let's start talking about structure of factors, and let's start with the univariate problem. Like many research areas in computer science and discrete math, this started with a question of Erdős 49. And the question he was interested in was the following. Suppose you are given a univariate polynomial, f of x, and it has t terms, it has t monomials. Then how many monomials can it square out? Is the question clear? You have a polynomial, it has t monomials, you square it, what happens to the number of monomials? What's an easy upper bound? How large can this number be? T square. It can be around t square. Can it actually be t square? Can you think of polynomials where it's actually grows as t square? Great. Other examples. Interesting ones. What do you need? What property of terms will suffice to give you this kind of a growth? Positive coefficients? That's not sufficient. Right. If you take 1 plus x squared plus x cubed, x to the n, square it, you only get 2 n terms. You don't get n terms. So one property that will suffice for this is that if the degree of the monomials is separated from each other. So if you take 1 plus x squared plus x to the 4 plus x to the 8 plus x to the 16, when you square it, you will see a lot of every pair is going to give you a distinct term. So that will so this t square bound, which is the trivial bound, is actually something that can be achieved. What's more interesting is what about lower bounds? So you have a polynomial with t terms, you square it. Can the number of terms reduce significantly? First of all, can it reduce? Or does it always reduce? Right, it can't reduce. Right, that's good. Yeah, so I mean, one of the questions he asked was, can the square have fewer terms than f itself? The answer is yes, it can. It's counterintuitive. And then, sure, I mean the number of terms might reduce. You may have a few examples, but then you ask, well, how much can it reduce? Can it reduce significantly? Can it reduce a little bit? We want to quantify the number of monomials in the square of polynomial. And here's an example. These examples are really annoying to find. So this is a polynomial p of x. I mean, it's a product of two things. I got Cloud to do the calculation, so I tried to make a mistake. So how many monomials does this guy have? This has 13 monomials. It has all, so its degree is 12, and every monomial of degree at most 12 has a non-zero coefficient. This thing has 13 terms. You square it, and you get this. And how many monomials does this have? 12. It does reduce. It reduces by 1, but it can reduce. Like I said, so I was trying to construct this. I knew that such examples existed. I wanted to construct this by hand. It was a very hard time. I couldn't get it. So I had to ask someone. So I asked Vishwas, who works in these things at IIT Bombay. He gave me this example. Gave me a bunch of examples. This seemed to be the least weird example that I could find. So such things happen. They are very counterintuitive, and so the second question starts making a lot more sense now. So there are clearly examples where the number of terms reduces, but you can ask, well, how low can this go? Yes.
If the smallest degree example.
I am not entirely sure. It may be. Amongst the examples I was given by Vishwas, this was the smallest degree one. But I suspect there may be lower degree numbers. I'm not entirely sure. I know that there aren't too many such. I mean, there aren't really too many such examples. We know some examples, but we don't have a recipe to cook up such examples on demand. It's kind of tricky to concoct systems. Is that okay? Good. Great. So the square can have fewer terms, and then we ask, well, how few? How low can it go? So Erdős asked this in 49, and something that I couldn't figure out was whether this paper came before this one or after this one. But Verdinius showed really an infinite family of such examples where f has t terms, but the square of f has t to the log 8 over log 13 terms. Okay, what is log 8 over log 13?
Less than 1.
It's some constant less than 1. So it can reduce polynomially. So there are infinitely many examples where the number of terms reduces polynomially. And you can take these examples and make some more, but I don't know what insight you gather in the process. I couldn't find the paper. I could only find statements, so I don't know what magic goes into construction. Okay, so these are examples where the reduction is fairly non-trivial. Like if t grows, then you are polynomially reducing the number of terms that you are actually going to see in the square. But then now at this point you can ask, well, is this a worst example? Are these the worst examples, or can you reduce? Are there families of polynomials where it reduces even further? Like, are there examples of f where the f has t terms and the square has log t terms? So that particular question remained open for many years. Till in the 80s, Schinzels showed that the square of f will have at least log t terms, roughly log t terms. But the best bound we know right now is from a result of Schinzel and Zanier in 08. It's relatively recent, and it improves Schinzel's original bound and shows that the square of f must have at least log t monomials. Can't go below log. Okay. As far as I can tell, this is the best upper bound we have, and I think this is the best lower bound we have. There's a big gap in this, right? This is growing polynomially with t. This is log t. There's an exponential gap between them. And understanding where the right answer to this problem lies is open. We don't know this well. We don't. I don't know if people have a good guess as to where the right answer is. Yeah. So Meanwhile, there have been further generalization to this of these theorems where you don't just talk about squares, you talk about arbitrary powers. You cube something, you take the fifth power and try to see how many monomials does the fifth power or something. And the answers look very similar to what we had. What about sparsity of arbitrary factors? So this is somehow about computing squares and square roots and cube roots, things like that. What about sparsity of arbitrary factors? This we know can be really bad, right? This is because of examples like this, where this polynomial has two terms and this has n terms. So yeah, so here things can be bad. But nevertheless, this question of understanding what happens to powers, it remains sort of open, not very well understood. I don't know if there's a consensus on where we expect the right answer to be. And we don't really have a lot of techniques for sort of standard off-the-shelf techniques for understanding these questions. There are plenty of things to think about here. Questions?
You said so pairwise sums are distinct, right?
Right.
So such things are related, right?
Yes. Yeah, the exponent vectors, they are called Zidane sets. Okay, but it's not just about cancellations can happen in coefficients. Yeah, that's what makes it. Okay, shall we go on?
How did the person come up with the 13-degree polynomial?
I have no idea. I mean, the answer to many of these things is by playing around with it. There may not be I mean, it's a degree 13 example, so there may not be some deep wisdom involved. But there will be some good amount of hard work tinkering with small. But I don't know. I'm speculating. I couldn't find. I tried. I was trying for lower degree 5 or degree 6. I spent a fair bit of time. Got something.
It's a basically question about I have a polynomial with me n, so that's n plus 1
Right.
variables, and then when I square it, I have 2n plus 1
Right.
possibilities, and then
Some of them might cancel out.
so then it's like if I want m of them to vanish, it's like m quadrants
Right. That's right.
vanishing and
Right.
it's
And you want common solutions. Right.
But there must be some sort of algorithms to sort of study points on.
Yes. So yeah. So you can throw some heavy hammer at these things and construct. Okay. Further questions? So now let's talk about multivariates. So now we are interested in similar questions, but for multivariate polynomials. Now we would like to understand say something about the structure of factors of a multivariate polynomial, assuming that the polynomial itself has some nice structure. And the setting here will be that n will be the number of variables, the degree would be some d, but think of d as poly n, think of d as n for everything that we are going to say. Recall that sparsity again is the number of non-zero monomials. And maybe the first question of interest, which is basically the question we ask for univariates, is to ask, well, what can we say about the sparsity of factors of a polynomial with sparsity s? If f has s terms, what can we say about the number of terms in the factors of that? And in particular, and this is a very computer science motivated question, where we would like to know if this number is the sparsity of factors is upper bounded by a fixed polynomial in S, meaning you can say that if f has s terms, then any factor of s will have s to the 10 terms, or s to the 100 terms, some constant, something that doesn't grow in s. And the answer to that is, well, no. For examples like this, so if you look at this polynomial, it has 2 to the n terms, so its sparsity is 2 to the n. But it factors into a product of these two things, and focus on the red factor. And this has, how many terms does this guy have? The red polynomial. It's like n to the n. Right? So it's close to n to the n, and n to the n is not a polynomial function of 2 to the n, it's n to the n. So it's a quasi-polynomial function. So So there are examples which suggest that, this is false. There is a little bit of cheating involved in this example, in the sense that typically when we talk about sparsity of factors, we really talk about sparsity of irreducible factors of polynomial. This one is not irreducible, but you can spend 5 minutes on this to take this example and construct a scenario where you get the same bound, but the big factor you're looking at is irreducible. It doesn't take much work. It's like annoying to write. Sorry. Good. So then for sparsity, we do expect some growth in the sparsity of factors, and the growth is not going to be polynomially bounded. So a very computer science, a complexity theoretic way of saying this is that sparse polynomials, the space of sparse polynomials, the set of sparse polynomials are not closed undertaking factors. So you take a sparse polynomial, factor it, you don't remain within the set, you get something that has a much larger sparsity. So one question to ask here is, how bad can this get? Can you construct examples where the growth in sparsity is more than this? So this is going from, so if the sparsity was s, this went from s to something like s to the log s. You can ask, well, can you construct things where this growth is even worse? Can you go from s to the s? Can you go from s to like 2 to the s to the epsilon? Things like that. Right? So can you get superpowers? Can you get exponential growth? And the answer is we don't know. We don't know if this is the worst example. This is the worst example we have. We don't know this is really the worst example. We don't know if it can get worse. We don't have things where the growth is more. Or we don't even know if there are fundamentally different bad examples. Basically, all the bad examples that I know of are based on basically what happened, the phenomena that happened here. So it's one of these strange questions where we have bad examples which tell us that the obvious, natural theorem we would like to show is false, but then we stop that. We don't really know how to say it. So it'd be interesting to do any of these things. Construct bad examples for this, which are fundamentally different. Something else is going on there. We don't really have that, or show that this is the worst that can happen. Or prove bounds on how bad can it get. So all possible directions in which you can ask a question here are open. They're not well understood, and we essentially don't have good ideas on how to approach this problem. People have thought about this for a while, and somehow we haven't found that way around it. Don't know how to say anything more interesting than what is happening. Okay, questions? Alright. Good, so sparsity is a bad notion of niceness with respect to closure under factorization. That was the conclusion of this discussion. So we can ask for other representation of polynomials. And we can say, well, instead of representing a polynomial by its non-zero monomials, let's write down all monomials. Even things with, so I tell you the degree of a polynomial, it can have so many monomials. Just write down every monomial with a lot of them with coefficient 0. So that's a representation. Oddly, that's called the sparse representation. The polynomial is really sparse, but it's embedded in a big block vector. So if f is n-variate, has degree d, the coefficient vector has length n plus d choose d. And if g is any factor of it, then it will have degree at most d minus 1. So clearly the length of the coefficient vector of g will not be larger than this because of the degree. Great, okay. So maybe this is the representation to use. It behaves nicely with factorization. What's the problem with this? It's too long. If p is like n, you're looking at exponentially many monomials. And almost the entire vector, if your polynomial happens to be sparse, is going to be filled with zeros. So this is a very, very redundant representation. And for computational questions, this is a mess. Most of the time, you'd like to compute polynomials. You would like to be far more efficient than something growing in 4 to 8. So even asking basic questions here becomes a problem. Great. So there were two natural ways of writing down multivariate polynomials. One was to write non-zero coefficients of the polynomial, and one was to write basically look at the whole coefficient vector. Most of it filled with 0. zeros potentially. And both of them have issues. Sparse, the first representation is not closed under taking factors. The second one is just too redundant and lossy. Alright, and polynomials, multivariate polynomials show up everywhere in computer science. They show up in algorithm design, they show up in crypto, they show up in error correcting codes, they show up in complexity theory. So we would really like a way of representing them that allows us to do computation with them efficiently. And what we need is a succinct representation. It shouldn't be, it shouldn't take us exponentially, a vector of exponential length to write a polynomial, especially polynomials of interest. But we would also like this representation to behave well with standard computational operations. Like if I want to evaluate a polynomial, this representation should let me evaluate it efficiently. If I want to add, multiply, divide, factorize, we would like this representation to behave well with these computational operations. And one such representation, at this point I would say the such representation is provided by what are called algebraic circuits or arithmetic circuits. So I'll tell you what they are. So we'll digress a bit. We'll talk about algebraic circuits and the complexity theory around them, and then we'll come back to factorization. Like 15 minutes. Okay. Great. So what are algebraic circuits? This is an algebraic circuit. This is a picture due to Ram Prasad and Claude. So, right. So this is what it looks like. What you have here is a bunch of variables and some field constants hanging around. And you have these internal vertices where you have product gates and sum gates. And they behave in the natural way. So the leaves compute whatever is written on them. And then a sum gate will compute the sum of things that is feeding into it. And a product gate will compute the product of things that's feeding into it. Right, so this gate over here computes the polynomial x2 times x3. This gate over here computes 3 times x2 times x3. This computes 3 times x2 times x3 plus I think x1 square. Is that okay? Is the idea clear? Great. So slightly more formally, these are directed acyclic graphs. This one is actually a trick, but in general they can be directed acyclic graphs. The internal nodes will have plus and multiplication on them, and there will be variables and field constants hanging out. There are two parameters of interest of such a representation. One is the size, which is like the number of vertices in this graph. So this graph has 3, 7, 11, 9 internal vertices and then a bunch of input vertices. So you can count whatever you want. You can count number of edges, number of vertices, everything is fine for this graph. The other parameter of interest of such circuits is the depth. So the depth is this is the output gate. This is computing the final polynomial. Depth is going to be the length of the longest path from this guy to any of the inputs, any of the variables. Okay, and intuitively, you should think of size in terms of efficiency. If I give you a circuit for a polynomial and I ask you to, evaluate this polynomial at x1 equals 1, x2 equals 7, x3 equals 9, x4 equals minus 7, and stuff like that, you can just plug in those values here and just let it propagate up. And you'll be able to find what the value of the polynomial is. And the amount of time this will take will be roughly polynomial in the number of gates you have. Every gate is like one arithmetic operation. So the number of the size of this graph is like it's something that captures efficiency of computation, of evaluation at least. The depth is captures parallelism in the sense that if I want to evaluate this polynomial, notice that I can do evaluations in the same layer at the same time. If I have different processors, things in the same layer can be evaluated at the same time. So the number of rounds that you are going to take will be, you first evaluate things here, then you evaluate things here, then you evaluate things here. You're done in 5 rounds. So depth captures parallelism. Great, and if you work out what polynomial is computed here, it is this polynomial. I didn't verify it. I wrote what Claude wrote. So it computes this, and the computation is very natural. Sum gate computes the sum of things, product gate computes the product, you let things propagate properly. Now, algebraic circuits are nice because they let you represent polynomials that may have many monomials in a very succinct and efficient way. For example, look at this polynomial. This is product over I going from 1 to n, 1 plus xi. How many monomials does this have? It has 2 to the n monomials. A lot of monomials, exponentially growing in n. But it has a very small circuit. Here is a circuit for this. So we have a layer of plus gates, then multiplication, and then further multiplication. And we have variables at the bottom. Each of these plus gates, this computes 1 plus x1, 1 plus x2, 1 plus x3, and so on. Then you multiply things together, you multiply further. Right? This is a very small, this is for n equals 4. You can do this for general n. And if you do this for general n, the same construction will give you a circuit of size 3n. That's the amount of resource it takes us to describe this polynomial, which has exponentially many monomials in it. The depth of these circuits is 3. So this polynomial, which has so many monomials, can be evaluated very, very fast in parallel. And if I ask you to evaluate this polynomial at any input, you're probably going to have a easier time using the circuit for this evaluation rather than writing this as a sum of monomials, evaluating each monomial, adding them up. And for computational questions, we will work with circuits. We do generally work with circuits as the model of computation. They have a lot of advantage over the first representation, first few representations you could think of. We saw 2 examples. One was to write a polynomial as a sum of non-zero monomials, and one was to write a polynomial as its entire coefficient vector. Circuits give you a succinct way of writing polynomials, and they behave very, very nicely with standard arithmetic algebraic operations. Great. So what's algebraic complexity theory? So algebraic complexity theory basically studies the complexity of computation of for algebraic problems. And often the model of computation here is going to be a circuit. We ask questions where our inputs are given as circuits, our outputs are given as circuits. We want to understand what's the complexity of some computation. Flavor of questions in this area are the various flavors. There's a question of upper bounds, which is maybe there's a polynomial you care about and you want to understand what's the smallest circuit computing this polynomial. The smaller the circuit is, you would have a faster way of evaluating this polynomial, for instance. We also ask questions about lower bounds, which is the question of understanding if the polynomial we care about can be computed by really small circuits. You want to say that maybe you're trying to optimize the circuit size for a polynomial of interest and you get stuck at some point. And at that point you would like to say that it can't get any smaller. So there's the question of lower bounds. Then there's the question of de-randomization. So I'll say in a minute what this means. But the question here, the flagship question here is the following. I give you 2 algebraic circuits. I give you 2 of these graphs. And I ask you, do they compute the same polynomial? And this is not as trivial as it seems. Why is that? Why is this not an obvious problem? If I give you 2 circuits, I ask you, do they compute the same polynomial?
Same polynomial might have different.
Right. The circuits might look wildly different from each other, and they might still end up computing the same thing. You may have lots of cancellations on the way. You might compute all sorts of things and then cancel them out. And eventually get to your problem. So this is a question. I say this is de-randomization because we have very fast randomized algorithms for these problems, and we would like algorithms that don't use randomness, that take the circuits, do something deterministic, and tell you if they compute the same. The other flavor of questions here are questions based on reconstruction, where this is, think of this as some sort of a machine learning based problem, where you are given access to a circuit. I have a circuit, I put it inside a black box. You have the power to query the circuit. You can give me inputs, I'll tell you what the answer is, what the evaluation of the polynomial of these inputs is, and based on this interaction, you would like to construct the circuit that I have inside the black box. So you would like to learn what model I am answering questions using. And then, of course, the problem that we started with, which is to understand the complexity of various algebraic operations. I give you 2 polynomials, I want to compute their GCD, I want to compute their factorization, I want to compute their derivatives, I want to integrate them. What is the complexity of these operations? So there are questions like this. Are we good? So these are some of the sort of main flavors of questions that people think about. The notice that, so I mean, two of the themes that people spend a lot of time thinking about are questions about low bounds and de-randomization. And seemingly they look like different problems. One is the problem of proving hardness, which is to show that there are certain polynomials that cannot be computed by small circuits. There are no efficient circuits that compute these polynomials. And the other is the question of de-randomization, which is, given two circuits, are they the same? Do they compute the same polynomial?
When we say small circuits, we are thinking in terms of size or?
We are thinking in terms of size, you can also think in terms of depth, you can take your favorite parameter. So the question of lower bounds and the question of de-randomization, these are two fundamental themes in all of computer science. We would like to prove that certain computational tasks of interest are hard. They cannot be done by efficient algorithms. And we would also like to show that problems that have efficient randomized algorithms can also have efficient deterministic algorithms. So hardness and randomness are two of the central themes in CS. And in the context of algebraic circuits, in the context of algebraic computation, the lower bound question is, you want to construct explicit families of polynomials that cannot be computed by circuits of small size. It's easy to show that such polynomials exist. The difficulty here is to construct polynomials that you can describe, that you can get your hands on. If you have heard of the P versus NP problem, this is like it's an algebraic analog of it. We also know that it's sort of a necessary immediate step. If you believe versions of the Riemann hypothesis, we know that to prove P versus NP, we need an answer to this question. We need algebraic circuit programs. The de-randomization question here is, so let me focus on polynomial identity testing. So this is a variant of the question that I mentioned in the previous slide. So here the setting is, so there the setting was, you are given two circuits, you want to understand if they compute the same polynomial. Notice that that's basically the same as saying I give you a circuit and you want to decide if it computes the zero polynomial. Why are these the same question? You take the two circuits, you subtract them, construct a new circuit and ask it if it computes the zero polynomial. Okay, and this has a very efficient randomized algorithm. You just pick some random inputs from a large enough domain and plug it into the circuit. In the circuit, if it computes zero, then you say the circuit computes the zero polynomial. If it gives you a non-zero value, then you know it computes the non-zero polynomial. You can show that with high probability over the choice of this algorithm. So there is a very, very efficient and simple randomized algorithm. We don't know if there is an efficient deterministic algorithm. So this is the question of de-randomization. And it's a very, very fundamental problem. It's a problem with many, many applications to algorithm design, to coding theory, to complexity theory, to a whole bunch of things. And some very deep connections, including to lower bounds, which seems surprising because this is a question about designing algorithms for something, de-randomizing algorithms for something. And this is a question about proving that something is hard to compute, and somehow they are very closely related to each other. Okay, so now let's get back to the question that we were interested in, which was multivariate polynomial factorization. And now we are going to ask this question in the context of our input and outputs being represented by circuits. So we would like to design an efficient algorithm that takes an n-variate polynomial, f of degree d, and it's given to us as a small circuit, and we'd like to output its factorization. Again, I want the output to be represented by circuits. We would ideally like ideally like to have polynomial time algorithms for this. But then if you want polynomial time algorithms for this, the first question you want to ask is, well, is it true that the factors have small circuits? Because if the circuit size of the factors is like exponentially growing in the circuit size of the input, there is no hope of getting a polytime algorithm. You can't even write out. And we already saw that this is not true for sparsity. If you were representing polynomials by non-zero monomials in them, then the complexity of the factor does grow super polynomially in the complexity of the input. Okay, great. So this is a very basic question, and it was studied in a sequence of papers in the 1980s, some by Kaltofen, Wagergarten, a bunch of people, and culminated in this amazing theorem of Kaltofen in the 80s, mid-80s. He showed that in this setting, when you have a polynomial f of degree poly n, and it has a circuit of size s, let's say S is poly n, then the factors also have circuits of size poly n. So the complexity of factors only grows polynomially in the complexity of the original polynomial and its degree. So unlike sparsity, the complexity of factors doesn't grow from the polynomial. Right, and it didn't stop there. He also gave an efficient randomized algorithm that actually solves this problem in green. He gave a randomized algorithm that takes a circuit as input and outputs, runs in time polynomial in the circuit size and the degree of the polynomial involved, and outputs circuits for all the irreducible factors. Okay, it's one of my favorite theorems. Okay, I'll wait here for 30 seconds if you have questions. Very good. Oh, well, it will toss some random coins. The guarantee would be that with high probability it will output to the right output. Yes, sir, you're asking what is the randomness used for?
Yes.
Yes. What is the randomness used for? It's used for PID inside. We didn't. This wasn't very clear in the 80s. It only became clear like 10 years ago. Okay, so shall we go on?
Final question.
Yes.
If you have a polynomial with like small enough coefficients, let's say,
Okay.
can we say anything about the root being small or something?
The root may not even be an integer or rational.
No, not rational, even if it is irrational or something.
What does small mean?
Small when compared to the coefficients, or like, is there a bound with coefficients?
Yes,
in the root?
there is a bound. There's a bound you can prove. I don't know if this bound will be good enough, but there's a bound you can prove. These are not hard, difficult bounds. Relatively elementary. There is a bound. Great. So let me restate Kartoffel's theorem. The theorem had two parts. The first part was a closure result. It told us that factors of polynomials with small algebraic circuits are small algebraic circuits. So in that sense, algebraic circuits, at least low degree algebraic circuits, are closed under taking factors. This is different from what happened for when they were writing polynomials in their as a sum of non-zero monomials. The other aspect of this theorem was an algorithm, which was an efficient algorithm that will take an algebraic circuit as input and with probability 99% output circuits for all its irreducible. So in the early 90s, in 92, this algorithm was extended by Kartoffen and Traeger to the black box setting. So this is quite amazing. So in this theorem, we have the input is given to us as a circuit. So you can look inside the circuit, look at what gate is connected to what inputs, what is the label, what are the constants, etc., etc. And you use that in your algorithm. In the black box model, all you are given is a black box access to the polynomial. So I don't let you see inside the circuit. You can give me an input and I will tell you what the value of the polynomial is on that input. And Kartoffen and Traeger showed that this access is enough to actually factorize a polynomial. So the guarantee here is that if I give you black box access to a polynomial, you can do some polynomial time computation with some randomness and simulate black box access to the irreducible factors of the polynomial. So if a black box is something you can copy, then you will take this black box and do some computation on top of it and output black boxes for the irreducible factors of this of the input polynomial. So almost seems unbelievable, right? It sounds false, but it's quite amazing. Even more amazing is that this theorem is not much harder to prove than the first one, which is shocking the first time I saw it. I think it's among the most profound results in all of TCS and adjoining areas of math. It's fundamental. It addresses a very, very basic question. It's extremely surprising. I don't think people expected closure of circuits at the time. It's one of these examples of a question where we asked the right question and we got an answer, and this happened in the 80s. It's quite amazing. In the process, so the sequence, so it's not one paper, it's multiple papers of Kartoffen and a bunch of other people. And these papers invented multiple new techniques. These techniques continue to be useful for problems of interest even today. And there are some amazing consequences to other questions. I will come to consequences. And it also helped settle this some debates, dinner table debates at least, about what the right model for computing polynomials is. So somehow it's circuits because they have all nice properties. They're even closed under factorization, which nobody expected. Nobody would expect in the first instance. Okay, good. So let me sort of change tracks a little bit for a minute and mention another theorem. So there's a theorem of, so I mentioned these themes of hardness and randomness. And there's a theorem of Kamenetz and Impagliazzo from 2000 which shows that you can use hardness to de-randomize polynomial identities. You can prove lower bounds for algebraic circuit. You can actually get deterministic algorithms for PID. So this is a connection between two problems that at the outset look very different from each other. They look problems of different flavor. And yeah, and this is a phenomena that keeps happening in computer science. Hardness and randomness, we keep on seeing connections between them, with connections going in both directions in fact. We know similar theorems in the setting of what are called Boolean circuits. And a crucial ingredient of this theorem is actually the proof of, is the closure result of algebraic circuits that I just mentioned. So this is one very, very killer application of Cartesian. So in fact, Kamenetz and Impagliazzo's paper has a section which says, why wasn't this result proven 15 years ago? And the answer is because not enough people knew about Cartesian. Great. So this is the 80s, and yeah, we already had an awesome theorem which answered many of the basic questions. So what was left? So there are two sets of questions that remained open, and these are largely the two sets of questions that continue to remain open mostly. The first question is that of de-randomization. So Cartesian designed a randomized algorithm for factorization. We would like deterministic algorithms for factorization. We would like an efficient deterministic algorithm for this problem, and we don't know how to do this. And in fact, we don't know very simple versions of these questions that we don't know. We don't have to do deterministic algorithms. And this is tricky because we now know that this problem is at least as hard as getting deterministic PID algorithms for circuits. And we know that PID algorithms for circuits have consequences to things like lower bounds. And some of those problems we expect to be difficult to solve. So somehow this chain leads to problems that we expect to be difficult. But who knows, maybe. A first step towards this problem would be to ask the same questions but for polynomials with even more structure. For instance, suppose that we give you a polynomial that is actually sparse, that only has n to the 10 monomials in it. And I give you the polynomial as a sum of coefficients. So you can actually see what monomials show up in the polynomial, what are the coefficients. And the question is, can we factor such sparse polynomials deterministically? We don't have great answers to this. We now have some answers to this, but they're not. We would like more. So the other flavor of questions that remained open at this point were the question of closure of other natural classes of polynomials. For instance, the kind of question we want to ask here is if the circuit for computing the polynomial has additional structure. For instance, it's small depth, which means that the polynomial has efficient parallel algorithms for evaluating it. Is it true that the factors inherit these properties? So we know that if the polynomial has a small circuit, the factors will have small circuits. But what about other properties of the circuit? If the circuit has low depth, do the factors have low depth? We again know, one has to be careful here because we know that at some point the answer to this question is no, because a very special example of a low depth circuit is when you write the polynomial as a sum of monomials. And at that point we know that the factors don't have small representations. Great. So this question about constant depth circuits has been of interest for a few years in the algebraic complexity community because people, and these are very natural class of circuits. They compute interesting things, and we would like to understand them better. Earlier last year we had some progress on questions of the kind of questions I mentioned. So with Bhattacharjee, who was at CMI a few years ago, Ramprasad Saptrishi was also at CMI. Rai and Ramanathan were PhD students at TIFR, and Shivangi Saraf at the University of Bangalore. We showed that if a polynomial has a small constant depth surface, so do its factors. So we knew that if a polynomial has a small circuit, so do its factors. But we didn't know if going from a polynomial to its factors can also preserve depth. And now we know that that's also true. So it preserves depth. Okay, so for sparse polynomials, what this means is, so sparse polynomials, if you think about it, is writing a polynomial as a sum of monomials is a depth 2 circuit. You're writing something as a sum of product of things. So we know that sparse polynomial does not have sparse factors. So we can't get depth 2 factors, depth 2 circuits for factors of sparse polynomials that are small. But we can get circuits, what this theorem says is that you can get a circuit of depth 10 for factors of sparse polynomials. That continues to be small. This was surprising to some of us at least. Okay, so this is the structural question. The question where we ask about the circuit complexity of the factors, and then we had this other question where we would like deterministic algorithms for this. We also had something interesting to say about that a couple of years back. So we had a deterministic algorithm. It's not an efficient deterministic algorithm. It actually runs in sub-exponential time. But this is the best we can do right now. So this is a deterministic algorithm that will take as input a constant depth circuit and output the factors, output constant depth circuits for the factors also. So that's the thing on the top is a statement about the structure of factors. The thing at the bottom is a deterministic algorithm that outputs the factors, which has a polynomial with constant depth circuits. Is that good? The statement here. Okay. I have 5 minutes. Great. So it's a slightly odd thing that the algorithm came before the structural algorithm. In the algorithm, we weren't able to argue that the thing we are outputting is a constant depth circuit. We could output circuits, and somehow the algorithm motivated some aspects of how this closure result was eventually proved. Good. Let me spend a few minutes talking about applications. One application is that you get a constant depth version of Cabinets in Pagliaro, the theorem I mentioned earlier. So that theorem was said that if you have low bounds for algebraic circuits, then you can use it to de-randomize PID. This theorem says that if you have low bounds for algebraic circuits with constant depth circuits, so what this means is if you can get your hands on explicit polynomials and show that they can't be computed by small constant depth circuits, then you can use such polynomials to design deterministic algorithm for polynomial identity tests. So we had results like this, and in fact that's how we know how to do PIT for constant depth circuits right now. But those results were not as clean as this. It's a cleaner and nicer statement. And there are other applications. We can use these ideas to design efficient parallel GCD computation algorithm for polynomials over finite fields, and do some other stuff, some other linear algebra stuff. Okay, so I had some technical slides, but I don't want to get into it. Are there questions? Good. I'll take 2 more minutes and tell you something about TIFR because everybody told me to go tell you something about TIFR. But I'll have to skip a whole bunch of slides.
This algorithm that you mentioned, Polynomial Factorization. So, is it based on some sort of Moore's theory or like induction in the variables?
Right. So induction in the variables is natural to do, but I don't know how to do it with circuits. So if you are given polynomials as a list of monomials, that's the first thing to try, and that can be made to work with some effort. With circuits, it's not an induction of the number of variables, but there is sort of a reduction from the n-variate case to the pi-variate case. Somehow so the univariate case is very different. We use so we have the univariate algorithms. They are a different family of algorithms. but they are used to solve the bivariate. Then you can lift from bivariate to multivariate.
So typically, like when you do it, when you like have a list, is like have a Grosvenor pieces,
Right.
and then you sort of take permutations of
Right. Right. So yeah, so we can't do any of the Grosvenor basis stuff here because yeah, there's not enough room. So the algorithms are not difficult.
It's more efficient.
Right. Somehow, yeah, somehow more efficient.
The key word is Hensel lifting.
Right.
That is
Some variants of Hensel lifting show up.
Oh, good, yes, we got.
Good. Thanks. The deadline is correct here. It's still 4th of April.